Hey class, hope everybody's doing well. I just wanted to take a little time this evening to go over the Skew-T log P diagram. I can recall back when I first learned how to read these diagrams, it wasn't easy, and it took some time to be able to decipher what's on them and just to learn the lines basically, and then to learn the how to read it with the data plotted on top of the chart. That's another step and was even more complicated. So it took me a while personally to learn how to read these diagrams. But that'll be the topic of this video. It'll be pretty short, but I wanted to make sure that everyone was on the same page with this. I've had some requests, and I'm so glad to be able to do this video to help out with that process, because I want everybody to do well with the Q2 exam. Obviously, that's wrapping up here in a couple days, as well as the midterm and coming quizzes and exams as well. So it's been a rainy, kind of dreary evening here in Starkville, Mississippi this evening. Temperature is holding right at about 60, 65 degrees, and significant rainfall, especially to our south, running from about Jackson to Meridian. But up here in Starkville, more just of a light, continuous rain is what we've got going. And we're so glad to have that, because it's been very dry here. Such a tremendous heat event over the fall, as I know many of you have experienced over the Deep South this fall. So finally some fall-like weather here across the South. Hope the weather is going great where you live, and everybody's enjoying the class. I'm going to try to make things as enjoyable as possible for you. So looking here at the task at hand, you can see this particular Skew-T log P diagram. Again, the mixing ratios, just in review, are these purple numbers here in grams per kilogram. And then they skew up and to the right, if you can see. Those are the saturated mixing ratio lines. And you use them, of course, to find relative humidity, as we've discussed in the previous video, where you will use the dew point for the just the mixing ratio, and then you'll use the temperature for the saturated mixing ratio. And relative humidity is found by dividing E by ES. So you'll do E divided by ES times 100 for your relative humidity. Okay, and so then for your temperature lines, your isotherms, those will be these darker reddish maroon lines right here. Here you can see the negative 20 degree isotherm up and to the right, minus 10, the 0, and 10, positive 10, and accordingly, and so on and so on. Okay, and one thing that it's important that some folks may be struggling with, I'm not real sure, is when you're plotting a temperature and dew point, and you trace up to the LCL height. Of course, you know that the dew point will go up the saturated mixing ratio line, or the isohume, and the temperature until saturation right off the surface will follow the dry adiabat. Okay, so you'll bring your temperature up the dry adiabat from the surface. Some folks tend to want to go to the nearest dry adiabatic line, the actual green line or whatever color the line is. They'll gravitate, say this surface temperature here is 13 degrees Celsius. Some folks will want to actually go over to the nearest dry adiabat, the nearest dry unsaturated adiabat, and follow that up. These lines here, all the lines on this chart are just here to guide you, okay? As I'm sure you've probably determined by now, those are just placeholders. They just kind of act as a general guidance as you trace up and you ascend up the Skew-T high into the atmosphere. Okay, so the values, the only reason why there aren't more lines on the chart, you could put as many lines on this chart for any of the values, mixing ratio, temperature, dry adiabat, moist adiabat, as you want, but then you wouldn't be able to see the diagram, right? There'd be no room left. And so those are just there to help guide you. You have to interpolate, so to say, or extrapolate, read between the two numbers or project out. But I'll just run through a couple of examples. Of course, you know these are the isobars right here, the solid horizontal blue lines. There's 1,000, 950, 900, 850, 800, and so on and so forth up the diagram. But what I would like to give you an example of is how to read. We'll just pick a point. We'll say temperature at 800 millibars. So the temperature at 800 millibars, here's 800 millibars. Find where that intersects the profile temperature, right? Because this is the actual profile temperature of the atmosphere. The temperature profile of the atmosphere is the far right line. The left is the dew point. And so the temperature here, make sure you find your isotherms. These skewed from bottom left to upper right, maroon lines, or whatever color they may be. On this diagram, they're all brown. This diagram's different, and I tried to overlay some color coding here to help you decipher what those lines are better. So there's a little legend down there for you. This may actually help some of you read it better. I'll zoom in on that so you can see. But I'll go back to the other diagram. So the temperature at 800 millibars, so there's where our temperature profile line intersects 800 millibars. And all we'll do from there is descend down to the surface the isotherm. And so you can see right here, it matches pretty well with the zero isotherm. So the temperature at 800 millibars for this particular Skew-T profile is 0 degrees Celsius. Okay? And say you want to find the dew point at the same, at 800 millibars. So you'd go right here. You can see negative 10 is here. You see 0 isotherm is here. Here's the negative 10. Come a little bit to the right. See, here's a situation where you have to interpolate. You have to use both the negative 10 isotherm and the 0 degree isotherm as guidance, and you have to read between. So it looks like it's about 2 degrees, a degree and a half, or we'll say 2 degrees warmer than negative 10 C. So we're going to say negative 8 C is the dew point at 800 millibars. Just bring that down to the surface. And you can tell this is the surface because at 1,000 millibars, because that's where the lines stop. The lines truncate down here at 1,000. So wherever that may be, out in the west, out on the high plains, that surface is going to be more up in through here, up at about 8,000 feet. Okay, and some of those high areas of eastern Colorado and New Mexico and places like that, Wyoming, you'll see that. But in this particular example, our surface, the lines stop at 1,000 millibars. Okay, let's do another example. Let's find the relative humidity at 500 millibars. So here's 500 millibars. Okay, first we need to find E. So our E is going to be, here's where 500 millibars, the isobar at 500 intersects the dew point. So that's going to be our E. So we'll drop down the saturated mixing ratio line. That's 0.1. Okay, then we'll find our ES at 500. You can see that the temperature profile, which is our E, going to act as our ES, intersects 500 millibars right here. Drop down that saturated mixing ratio. You see 1. So you're going to want to do 0.1 divided by 1. Okay, and that's going to give you 10%. So 10% relative humidity in this particular sounding at 500 millibars. Okay, so I hope that helps. I'll go ahead and do one more example. Let's find at what pressure. I'll ask this a little bit differently. Sometimes these questions are phrased differently. Like I think some of them are done this way on the midterm exam. At what pressure is the temperature minus 20 degrees Celsius? Okay, at what pressure? So we'll go up the temperature profile and we'll find minus 20. See right here, this is the minus 20 isotherm. Go up that, find where it intersects the red temperature profile line, this line here. You can see that's right here. And that's between 500 and 550 millibars. So 525. 525 millibars would be the pressure level, the pressure surface or level at which the atmosphere is at negative 20 degrees Celsius. Okay, So let's review some of the lines one more time and what they mean. Here are your saturated adiabats, these dashed curves right here. Let's follow that. Here's another one. Okay, and we'll do one more here. And one interesting thing I'll point out is notice that down low and further to the right on the diagram, this of course being more right and this more left, further to the right on the diagram, the dry adiabats, which are these, they look like kind of like slides. See, they have a very low slope, little slope at the bottom and greater slope at the top. See, whereas the saturated mixing ratio lines, the wet adiabats, have a very steep slope. They're pretty much vertical down low, and then they lessen with height. Okay, especially more to the right of the diagram. But notice that the saturated adiabats have a different shape over here than they do on the left side of the diagram. And the reason for that is what we call pseudo-adiabatic processes. You guys are probably familiar with that term. I think we've used it throughout the semester some. Over here you have more moisture, right? So you have more potential for latent heat release. All right, and so you're going to overall stay warmer when you have more moisture on the right side of the diagram. But as you move to the left side of the Skew-T diagram, Skew-T log P diagram, you don't have as much moisture to release latent heat of condensation, etc. Fusion, all that good stuff. And so the slopes of the moist adiabats, the dashed green lines here, and the dry adiabats, the solid slopes here that my cursor hand is on now, are about the same. Whereas over here, they're not. You see what a difference they are here? It's a big difference. Okay, so that's one interesting thing I wanted to point out to you. But a couple of the big things elsewise I wanted to cover, I think that's going to pretty much wrap it up. I'll go over one more diagram. You guys have seen this one on the exams and quizzes. This is from the University of Wyoming. This particular date was the 27th, the evening of April 27th, 2014. And there was an ongoing tornado outbreak across northern Arkansas and southern Missouri. A horrific EF4 tornado struck near Mayflower, Arkansas, on the north suburbs of Little Rock, there, the capital, and roared through Valonia and Mayflower, Arkansas, causing horrific devastation. This is the atmospheric proximity sounding that captured that event. So you can see here the mixing ratios, again in purple. They're not always going to be that way, but on these few diagrams we've looked at, they have been. 0.4, 1, 2, 4, 7, 10. I believe that's a 15 or a 16, etc. Probably a 16. But let's work right in through here for a minute. We'll go ahead and just review how to calculate relative humidity. We'll say again for, we'll go ahead and pick 800 millibars this time. Let's go a little higher. Let's say, let's go ahead and do it for 650. We'll do it for 650 millibars. Okay, so we have 4. Our E is going to be 4. So we're using the dew point, descending back down the saturated mixing ratio line to the surface. We know this is the surface because the sounding terminates. This is where it first starts right here. So that's surface. Okay, so your 4 here for your E. And then for your E sub S, we're going to have, it looks like you have to interpolate, right? So it's halfway between the 7 and 10 roughly, a little bit closer to the 7. So we'll say, we'll go ahead and call that 8, just for the sake of brevity. So you're going to have 4 divided by, it looks like 8. So that's going to be 50% relative humidity, approximately at this level. Okay, that's kind of a rough estimate because of the way this dew point contour is kind of flattened here. But now you see that's definitely the way to do that. Okay. And these slopes, green slopes right here, are going to be your dry adiabats, unsaturated adiabats. These blue lines right here, that's a familiar slope to us. That's the moist adiabats or saturated adiabats. Again, your pressure lines are like this. So I'll go ahead and we'll do a little exercise. Find me the temperature at 600 millibars. Go ahead and you can either pause it or you may already know it just by glancing. But we'll go to 600 millibars. Remember, this is our temperature profile. It's the rightmost line, deep, dark, black line here. Dew point is on the left. So 600 millibars, temperature. Remember, these are your temperature skews. Minus 10. This would be minus 5, right? 0. Okay, all the way up. So temperature at 600 millibars, that would be your 600 millibar line. Isobar is right here. Your dew point intersects that here. Let's come back down the isotherm. So it looks like minus 1, perhaps at 600 millibars. You notice how we're not descending that line, the isotherms, directly along the line, because then we'd be wrong. Okay, it doesn't quite tie in to the temperature profile line, which is this line, at 600 millibars. It's a little above it. Okay, so we'll need to, there is the exact intersection at the tip of the arrow of 600 millibars and the temperature profile line. Atmospheric temperature, observed temperature profile. So then we'll come down a little bit to the left of the 0. That's how we're getting the minus 1. Okay, and we'll do a dew point example again, just because I want everybody to do really well. Let's go ahead and take the dew point temperature at 400 millibars. So here's our 400 millibar ISO, excuse me, it's been a long day. Your isobar, there we go. Okay, 400 millibar isobar right here. You can see that it ties in with 400 millibars, the dew point profile, right here. Okay, and so we'll then descend down the isotherm. You can see that our dew point at 400 millibars is minus 28 or 9. Okay, again, coming from up here and then just dropping on straight down. Looks like about minus 29 to me. Okay, and we won't mess with these right now, but here's your atmospheric winds. If you'll just tack on a little arrow, like imagine there being an arrow on each one of these little barbs, okay? That showing you which way the wind is blowing. All right, if you can just imagine that. So this would be like a wind out of the southeast. This is more of a wind out of the west up here. We won't go too heavily into that right now. I mostly wanted to cover the Skew-T log P diagram and how to read things. That's really important. I know we're going to go more into that later. So again, you have the saturated adiabats, the moist adiabats. Those are at a greater angle on the right side of the diagram. They're more parallel over here. As you can see, they're almost exactly parallel. And one thing I'll mention, when they become more parallel on the right side of the diagram up here, that's when all the latent heat has been released. So if you ascend a parcel of air up from its point of saturation and you raise it up to where the saturated adiabats and unsaturated adiabats become parallel, oftentimes that's between 200 and 300 millibars, you can see right in here, and then you bring it back down dry adiabatically to its point of origin, its level of origin, that's theta E. That's how you find equivalent potential temperature, which is, as you may know, an extremely useful metric for forecasting tornadic thunderstorms, severe weather. Okay, over here you can see that happens really low because there's not much moisture to condense out, much latent heat to release. Okay, so I sure hope that helps everyone. My heart's desire is for everybody to nail these exams, quizzes. I really want that to happen. You guys are doing great. If you have any questions, just shoot me an email. I'll be around waiting to hear from you. So y'all take care and have a great evening.